Hello, we're starting a new topic today. We have power series solutions of linear second order ODEs with non-constant coefficients. So usually those coefficients are polynomials. So we have P of x times y double prime plus Q of x times y prime plus R of xy equals 0. And usually, as I say, we're thinking of P, Q, and R as polynomials. So we don't know how to solve that by our technique of the characteristic equation. We need constant coefficients for that. All right, so we have two sets in this topic. Set 14 is a review of series, power series, and Taylor series. And today I'm going to talk about problems 1 through 5 in that set. And it's due on Thursday night. It's kind of a non-standard for our class, but we're not really tied to our Tuesday, Thursday class anymore. We're totally asynchronous. So this is about half the week. We had one due on Monday, next one's due on Thursday. All right, then the next set after that, we'll get to the series solutions proper. Okay, so this is our review, but it was kind of a tough topic in Calc 2. So let's remember the Taylor series of a function f of x. The Taylor series of that function about x equals a is called the center, is that f of x equals the sum from n equals 0 of Cn, the coefficient, times x minus a to the n, where Cn is the nth derivative of the function evaluated at the center a divided by n factorial. And that's an infinite series, but if we truncate it, if we stop with x minus a to the d, we get the Taylor polynomial of degree d. Okay, we'll do some examples of that. So let me rewrite this and summarize it. We'll summarize it in a way that we often use, that f of x is f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared plus f triple prime evaluated a over 3 factorial times x minus a cubed plus dot dot dot. Okay, so remember, to get that, you have to remember that 0 factorial is 1 and 1 factorial is 1, and then something like 5 factorial is 5 times 4 times 3 times 2 times 1, right? Okay. The other thing that is maybe not clear is that the 0th derivative of the function is just the function itself. So this is actually f super 0 evaluated a over 0 factorial. And that's just a function divided by 1. Okay, and then for this guy here, we might say T1 of x would be f of a plus f prime of a times x minus a period. That would be the Taylor polynomial of degree 1. It's a linear function, and this is in fact called local linearization. Which was one of the most important topics in Calc 1. We can approximate any function that's differentiable near the point x equals a by the tangent line approximation. And then T2 of x would be this, but I keep going. Okay, and then I have to divide by 2. Oops, sorry. I have this same term, but then I add the second derivative at a over 2 times x minus a squared. Let's make this a little prettier. this is a local quadratic fit. It's not the best linear function, but it's the best quadratic fit. So if you're near x equals a, this is the best quadratic function, the best parabola. It looks a lot like the graph of f. In fact, tomorrow we're going to use this to say, find this, approximate the square root of 101, say. Local linearization is pretty good, but this is just really awesome. We'll see that next time. So let's do an example. Find the Taylor series of f of x equals x cubed minus 2x plus 1 about x equals 0. This is also called the Maclaurin series. M-A-C-L-A-U-R-I-N series. And then we can just put a period. If we say Maclaurin series, that means the center A is 0. In fact, we almost always do that. And then we just have that f of x is going to be f of 0 plus sum from n equals 0 to infinity, f, take the nth derivative at 0 divided by n factorial times x to the n. All right. So let's compute these coefficients, these guys, Cn. Okay, and in general, you evaluate the derivative at a. Okay, so let's make a little table here, n, and the nth derivative at x. Okay, so n is going to be 0, 1, 2, 3, 4. Then we find write the function. The 0th derivative is the function itself. This is x cubed minus 2x plus 1. The first derivative is 3x squared minus 2. Second derivative is 6x. Third derivative is 6. Fourth derivative is 0. In fact, the fifth, 6th, 7th, all the rest of them are also 0, right? Okay. Now we want to evaluate the derivative at 0 because it's a series about a equals 0, or the Maclaurin series. So this can be pretty easy to evaluate. That's 1, negative 2, 0, 6, 0, 0. And then we have Cn. There's Cn. I take this number divided by n factorial. 1 over 0 factorial, that's 1 over 1 is 1. And here we have negative 2 over 1 factorial, that's negative 2 over 1, that's just negative 2. And here we have 0 over 2 factorial, that's 0. Then we have 6 over 3 factorial, that's 6 over 3 times 2 times 1, that's 1. And then we'll have 0, 0, etc. Okay, so we found that C sub 0 is 1, C sub 1 is negative 2, C sub 2 is 0, there's C sub 2, C sub 3 is 1, C sub 4 is 0. So if I put that together up in this formula up here, we get that f of x is 1 plus negative 2 times x plus 0 times x squared plus 1 times x cubed plus 0 times x to the 4th plus 0 times x to the 5th plus 0 times x to the 6th plus, I do have an infinite number of terms here, but they're all 0 from then on. So that can be more simply written as 1 minus 2x plus x cubed. Okay, well, so look at this. The original function was x cubed minus 2x plus 1. I just wrote the terms in opposite order. That doesn't matter. So this is kind of a silly problem to do, but it's also a very illuminating one. So what it says is, this function, as weird as it looks, is just what it has to be with that n factorial and all that. Just what it has to be to make this equality hold, for polynomials, okay? For a polynomial is exactly equal to its Taylor series. You can't help it. It has to be. Okay. But let's go on, think about the same function, and let's do another, oh, right. Well, let's also think about the radius of convergence. Where does this power series converge? Everywhere, for any x, right? Right? It's an infinite number of terms that are all 0. So it converges everywhere. That's radius of convergence equals infinity. And I think you're right. Capital INF, yeah, in web work. Okay. So let's do the same problem, the same function, but let's find a Taylor series about x equals 1. Oops. Okay, so with the table we've got so far, this doesn't change, but this all does. So the derivatives at any x, it's just a property of the function, but now we want to evaluate the nth derivative at 1, because a is 1. So 1 minus 2 plus 1 is 0. 3 minus 2 is 1. 6 times 1 is 6. 6 is 6, and 0, etc., 0. Okay? So now I find Cn to take that number divided by n factorial. I'm not going to go through it as much detail as I did before. That's 0. Here's 1 over 1. Here's 6 over 2 factorial. That's 3. And then here's 6 over 3 factorial. That's 1. And then here's 0. So the coefficients now for this guy are going to be 0, C0 is 0, C1 is 1, C2 is 3, C3 is 1, C4 is 0. So what we found here is that this function can also be written as 0 plus 1 times x minus 1 plus 3 times x minus 1 squared plus 1 times x minus 1 cubed. Okay, or getting rid of the zeros I don't need. This is going to be x minus 1 plus 3 times x minus 1 squared plus x minus 1 cubed. And that's non-trivial. The fact that these functions are the same would be kind of hard to say. If I just asked you what coefficients to put in for the sum of c and x minus 1 to the n, it would be hard to see. And this actually sometimes does have value to do this calculation. Okay. That being said, all right, what's radius of convergence? That's still going to be infinity. Okay. That being said, for the rest of these problems, we've done problem 1 and 2 now. For the rest of them, we actually don't use this formula. This formula here is, I sometimes call it the dangerous formula. It should only be used if necessary. It's good to have it. It's like a fire extinguisher in your house, right? You don't want to use it unless you have to. Okay, so we're going to we're going to be talking about a lot of techniques for avoiding using that formula. And the first one is has to do with the geometric series. You might remember that if I have A plus AR plus AR squared plus AR cubed plus AR to the fourth plus dot dot dot. This is a geometric series, first term A. And it's different from the center of the series. Oh well. And then it has ratio R. So every term is R times the one before it. Right? So this thing you might remember is the first term over 1 minus the common ratio. And this holds provided absolute value of R is less than 1. If R is 1, I'm out of luck because I'm dividing by 0. Can't do that. If R is negative 1, it doesn't really converge. If R is negative 1, you get A minus A plus A minus A plus A minus A, and that, remember, it doesn't converge. Okay. So why is that useful? Well, let's let A be 1 and let R be X. So then I get 1 plus X squared plus X cubed plus X fourth plus dot 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 equals 1 over 1 minus X. So in fact, if I turn this around, that means that if f of x is 1 over 1 minus x, that has the Taylor series, or the Maclaurin series, 1 plus x squared plus x cubed plus x fourth plus dot dot dot. Right? I have C0 is 1, C1 is 1, C2 is 1, C3 is 1, etc. And the radius of convergence now, R, is 1, because this converges, since the power series PS converges for absolute value of x less than 1, and it diverges if absolute value of x is bigger than 1, okay? So let's use that to do something like one of your problems. Suppose I have find the Maclaurin series of f of x is 3 over 2 minus x. Okay, well, A equals 3 kind of works there. And you notice the A is there, but this isn't 1 minus something on the bottom. So what you have to do is you have to massage this and write it as 3 times 1 over 2 minus x, or 3 times 1 over 2 times 1 minus x over 2, right? See that? Or 3 halves times 1 over 1 minus x over 2. So that means I can, actually maybe given this, I'll write this as 3 halves on top over 1 minus x over 2. So this is exactly a geometric series with the first term A is 3 halves. It's like this. With that R there, R is x over 2. All right? And again, I'm putting the f of x on the left. So we have 3 halves over 1 minus x over 2 is 3 halves plus 3 halves times x over 2 plus 3 halves times x over 2 squared plus 3 halves times x over 2 cubed And they want C4, so I can stop here, plus 3 halves times x over 2 to the 4, plus dot, dot, dot. So I can collect all these terms here. So what is a coefficient? So let's rewrite this. This is 3 halves. That's C0, the constant term is 3 halves. And then this is going to be 3/4 times x. So C1 is 3/4 plus 3, 2, 4, 8, 3/8 times x squared. C2 is 3/8 plus 3/16 times x cubed plus 3/32 times x fourth plus dot, dot, dot. So I can fill them in. Here is 3/16, and here is 3/32. Okay, and what is the radius of convergence? Well, this thing holds, this equality holds, provided its absolute value of r is less than 1. And what is the r here? It's x over 2. So if the absolute value of x over 2 is less than 1, the series converges. Or we can write this as absolute value of x is less than 2, right? So this is, that number there, that's the r, radius of convergence of the power series, right? Power series always converges as a power series centered at 0 will converge if the absolute value of x is less than r, diverge if the absolute value of x is greater than r, and if the absolute value of x equals r, it can do either one. But that's one of the subtleties actually nicely we don't really worry about in this class. We talk about it a lot in Calc 2. All right. Let's see. Let's do one more little trick. Actually, we've done 4 out of 5. One more little trick. Let's do f of x is, say, 3/5 plus x squared. Okay? Okay. Actually, maybe I'll do it a little bit more like one of yours. Let's do, say, 3/1 plus 9x squared. Okay, so let's do that. Well, this is actually, in a way, closer than the previous one is to our geometric series. This is 3/1. Oh, I want 1 minus. Well, I got 1 plus. Oh, that's okay. It's 1 minus negative 9x squared. Ooh, cool. So this is still another geometric series. The first term, a, is 3. The common ratio, r, is minus 9x squared. Right? So the common ratio is that number there, so the form, right? So the form a/1 minus r, right? That's what I'm looking for. I'm trying to make it look like a/1 minus r. So there, the r is negative 9x squared. So I get that 3/1 plus 9x squared is a 3 plus a times r minus 9x squared plus a times r squared minus 9x squared all squared. And actually I can stop there. Oops, I said a is 3, so make that a 3. Okay, so what is that? This is going to be 3 minus 27 x squared. Ooh, 81. And there's going to be a plus sign now. 3 times 81. 8 times 3 is 24. 241 plus 241 x to the 4 plus dot, dot, dot. Okay. Okay. 81 times 3. I'm not sure. 243. You're probably, I could hear you yelling at me through YouTube. 243. All right, and there's a plus sign. You notice that I don't see it, but there's a plus 0x here. There's a plus 0x cubed here. I don't see them, but that means the coefficients here, C0 is 3. C1 is 0. The coefficient in front of x is 0. I don't see it because it's 0 times x. Coefficient in front of x squared is minus 27. Coefficient in front of x cubed is also 0. Coefficient in front of x fourth is 243, after I did the multiplication right, okay? And I guarantee you, well, I don't know, maybe I'm telling you well, but in the past, these zeros have been what everybody sends me email about the night before the web work is due, okay? It's not the first term, second term, third term. It's the coefficient of x to the 1 and coefficient of x to the 2 and coefficient of x to the 3. And if I don't see it there, that coefficient is 0, right? Okay. So, but let's think about R. So this holds. This geometric series converges and the equality holds. Converges provided absolute value of R is less than 1. In this case, its absolute value of minus 9x squared is less than 1. Okay? So write that down. Don't try to do too much. It's just the absolute value of R is less than 1. Okay? In this case, R is minus 9x squared. Well, the minus sign inside the absolute value doesn't do anything. So this is also 9x squared. That's what the absolute value of minus 9x squared is. X squared is always positive or maybe 0. So I can get rid of the absolute value. It's just 9x squared less than 1. Okay? Or x squared less than a 9. Or absolute value of x is less than a third. Okay? You see that? X squared is less than a 9, so absolute value of x is less than a third. So that means the radius of convergence R is a third. Okay. All right, so that's like I say, you should be able to do problem 1 through 5 now. And a little hint in problem 3, recognize problem 3 is a geometric series. All right. So, so next time we're going to be doing some more stuff. We're going to be talking about how you deal with things like e to the x, functions like sine and cosine, arctangent, other functions like that that have known series. Again, we're not going to be using that dangerous formula much. We're going to do as much as we can to avoid actually computing the nth derivative of f evaluated at a divided by n factorial. All right, well,